Okay, hello everyone. My name is Jacob Pardue. I am the Group 2 lead for the bomb calorimeter. Hope you guys are doing well, and I want to preface this with I know that this is the wrong experiment. Earlier in the year, I did the wrong experiment uh, 1 week, so this is making up for that week. Okay, starting off the goals of the experiment, there are three main goals of this experiment, and it's going to be familiarize yourself with the principles, procedures, and techniques of the bomb calorimeter. It is also to find the thermal capacitance of the calorimeter and determine the heat of combustion of the two samples that we will be combusting. And on to the thermodynamic background of the experiment. A quick explanation of heat of combustion. It is basically the number of heat units liberated by a unit mass. So it's basically how much heat a specific material will give off when you combust it. And it is observable through a constant volume system. So by combusting the fuel sample and observing the temperature change of the system. The basic equation is Q is equal to mCV delta T, where Q is the heat of combustion, M is the mass, CV is the specific heat, and delta T is the change in temperature of the system. Okay, and some applications of this theory is it's used to compare heating values of fuels. So this can be useful for fuel costs, economics specifically. It is also used to determine the stability of the fuel, so safety and energy production as well. And some industries that use it are oil and gas, automotive, aerospace, many more. My personal favorite is automotive, little IC engine over here, internal combustion engine, which uses heat of combustion and different fuel types. And their heat of combustion is very important in the automotive industry. Okay, on to the apparatus of the experiment. We'll be using a PAR oxygen bomb calorimeter with the major components being the bomb casing at 2 and 3. So basically this whole structure here. The ignition wire will be connected from the electrodes right here to the fuel sample. It'll be running directly into the fuel sample. The water bucket and the thermocouple with the bomb placed in the water with the thermocouple, and then the stir to keep the uniform temperature throughout the water after the explosion. Okay, and a quick procedure overview. You're going to place the fuel sample in crucible. The crucible is basically just the thing that holds the fuel sample right here, 1D. And you're going to seal the bomb and remove the oxygen. This is done by pressurizing it with pure oxygen and then purging that pressurized bomb container about 4 or 5 times until enough of the fluid in there is oxygen and not oxygen combined with air. Then you're going to attach the igniter and place the bomb in the bucket, insert the thermocouple and stir, and then you're going to ignite the sample with the stirrer turned on, of course, and then observe the temperature change after the combustion. And then you're going to repeat it for the second fuel sample, which is unknown, which, surprise, will be Sour Jacks. Okay, and some predicted results, basically including thermal capacity and temperature rise of the water. Starting off with the thermal capacity of the stainless steel and the water combined. So thermal capacity is basically equal to mass times specific heat at constant volume. So that's actually supposed to be CV, although I don't think it matters for fluids and solids, if I remember correctly. Yeah. So assuming 2 kilograms of water, 3 kilograms of stainless steel, and finding the specific heats offline. For stainless steel and water, you can calculate the combined thermal capacity of both the water and the steel. It comes out to be about 9,879 joules per Kelvin. And the thermal capacity is equal to dQ over dt. So solving for dQ, integrating, and you'll find that Q is equal to 9,879 times delta T. It's joules per Kelvin times delta T for the stainless steel in the water. Okay. And on to the predictions of temperature change. So we're going to assume that heat leaving the system is 0. So the only heat within the system is the heat generated from the explosion. So setting the heat of the steel and water equal to the heat of the benzoic acid produced whenever it combusts, and also pulling benzoic acid's heat of combustion offline as well. You can solve for the delta T, which is about 0.37 Kelvin or Celsius. And some uncertainties of the experiment. Some points of uncertainties can be from the thermocouple, of course, as every experiment with the thermocouple has uncertainties for the thermocouple. And uncertainties in the measurement of the weight. So this is things like the water, the stainless steel could have uncertainties, the fuel sample could have uncertainties, and length uncertainties, especially in the ignition wire. It's also important to note that there might be some uncertainties because the contribution of the wires, the contribution of the wire to the heat of combustion and all the calculations is also negligible. And here are some of my references. And that is it. Thank you guys for watching and stay safe.